So let's just put these all down and see what the Kaya identity actually is. So the idea is, of course, that we are interested in global average temperature. And so that is going to be connected to the human-caused emissions of greenhouse gases like carbon dioxide. And the dominant area that creates emissions of CO2 as far as humans are concerned is from our energy sector. So the production of energy for basically all of our economy. So we have human-caused CO2 emissions from energy are related to global temperature. The more emissions, the higher the temperature. And so what are our four categories? Our four categories are, number one is just the number of people on the planet. So basically more people, more CO2 emissions. Not because people breathe CO2, but because people use energy. So that's our first term, population, number of people on the planet. And in this equation, that gets multiplied by the goods and services consumed or produced per person. So that's just GDP, global GDP, all of the goods and services that that collectively the global society produces and or consumes per person. So GDP per capita globally. Multiply that times the energy required to produce a given amount of goods and services. So if we could produce all of our goods and services without using energy, which is impossible, then we wouldn't have CO2 emissions. If we didn't consume anything, we wouldn't have CO2 emissions. And if there were no people on the planet, we wouldn't have CO2 emissions. And then our last term is CO2 emissions for a given amount of energy produced. So that is, these last two terms are the ones that we've talked about in different phrasing. So this last one would be the decarbonization term, that if you take out the amount of carbon that's produced for a given amount of energy, that would be decarbonizing that energy. And then this third one, energy required to produce a given amount of goods and services, is like our energy efficiency. It's kind of, you reverse the numerator and the denominator from how it's usually done, because you'd usually think about it as like dollars per joule of energy, but here it's joules per dollar. But you can see how this then equals human-caused CO2 emissions from energy. And it's an equation in a true sense. So it's not just here's four categories and that's, just conceptually by itself. It actually is an equation where, like, if you put in a 0 for any one of these, then you get 0 CO2 emissions, and then that's going to mean that global temperature is not going to rise. So here are kind of some trends for these things. These are some projections out to the year 2100. These are kind of mainstream projections from the United Nations and various modeling groups that do this. And so let's just look at these projections. So this first one is global population. So they said this in the video, that global population is growing. And so we're currently around 8 billion people. And as we talked about a couple lectures ago, at least the growth rate of population is decreasing and expected to reach 0. The growth rate is expected to reach 0 by around the end of the century, which would mean that total population would level off. And the current kind of central projection is around 11 billion people. So that is going to be a trend in the more CO2 direction, more people, more CO2. And then we have this goods and services consumed or produced per person, so GDP per capita. And that's growing steadily as well. And it's especially driven by what is a very good thing, which is the material well-being of people in the developing world is increasing, or is expected to increase quite a bit this century. So rapidly developing economies in China, India, South Africa, Mexico, Brazil, Indonesia. So these are higher standards of living for people on the planet. And you can kind of just get a sense of this, that it takes more energy to be a rich country than a poor country, right? So if you look at the kitchen of a high GDP country versus the kitchen in a low GDP country, we just have like way more things that all required energy to produce, and then we run them on more energy as well, right? So if you have a microwave or you have a Keurig or a refrigerator and a stove and running water, all of that is using energy. And that's very good for humanity, for people to have access to those things. Where in low GDP countries, they don't have nearly as many of those things. And so even though their energy efficiency might be lower, there's much less total energy consumed in these countries. And so we are expecting that situation to improve a lot in terms of there being more energy consumption for people, which makes their lives materially better. But that is going in the opposite direction of what we want in terms of CO2 production. So that's why that thing is going up over there. Then we have the energy efficiency one. That's energy intensity of GDP. And that is actually, it has been decreasing, which is good. And it's expected to continue to decrease. So because the numerator and denominator are flipped from the way we normally think about it, it's good that it's decreasing. So this is essentially that we are getting more efficient in our energy consumption. So less energy per unit of economic output. And we can just think of that like, we have more efficient cars. Like, so if your miles per gallon is, increasing, you can go further for a given gallon of gas. That's an improvement in energy efficiency, which would be a decrease in energy intensity. We can, heat, if we have better insulation, for example, we can heat our buildings with less total energy consumed. So that would be an increase in energy efficiency. Economies shifting from manufacturing to services. Think about like the modern economy, the way that we measure GDP, it's any good or service exchanged for money. So if you're buying like consulting services, you're buying software or something, there's a lot less energy embedded in those types of services than there would be for buying a thing like, I don't know, a tractor or something. And so since we have more of the economy kind of shifting towards services and away from things, that's also helping our energy intensity of GDP. It takes less energy for a unit of consumption or production. Another way to think about that is just the increased efficiency of our technology. So this is just kind of a visual example of, you think about a smartphone in 2020, that this replaces something like, a dozen or 2 dozen devices from 1990. So here's a Radio Shack ad from the early 90s. And, there's so many of these kind of electronic devices that are embedded within this smartphone. So you have a computer, you have a phone, this is a CD player, like ham radio, cassette player, calculator. Plus it has a bunch of other things that never, did not exist, of course, in 1990. And so that shows that you can get a lot more services for a unit of energy, because you don't have to have all of these additional machines in order to get those services. But this also kind of brings up that rebound effect that they talked about in the video, that not everyone, more people have smartphones now than had all of these devices in 1990. So it's kind of only if you were really into it or really rich in 1990 do you have a house full of these electronics, where now a lot more people have these things. So as the efficiency gets better, then it gets a wider adoption. And so that can kind of cancel out some of that increase in efficiency. So these first three things together, population, GDP per capita, energy intensity of GDP, if you multiply those together, that is the total amount of energy used by the global economy. And so you can see how that works out like mathematically, that these cancel out. You have people in the numerator, people in the denominator, GDP in the numerator, GDP in the denominator, and what's left is just energy. So we can see from this that there's this trend in energy increasing, basically because there's more people, you're getting more and more people, and more growth economically. So more GDP per person. And that's canceled out a little bit by increases in efficiency. So then our last term is what we call the carbon intensity of energy, or the amount of carbon dioxide emitted by energy use. And so amount of CO2 per unit of energy. And that is kind of in a baseline scenario, expected to gradually decline as we shift from burning fossil fuels, coal, oil, and natural gas, towards wind and solar and geothermal and hydropower, things that do not emit CO2 as a byproduct. So these are kind of just baseline projections without strong climate policy globally. And so this is expected to gradually decrease. But if you multiply all these things together, this is what we get for carbon dioxide emissions over the rest of the century. And so that's just showing increases and increases and increases throughout the remainder of the century for carbon dioxide emissions in this future scenario without strong climate policy. And of course, this is emissions, gigatons of CO2 per year. So that's the flux into the atmosphere. So these not only have to plateau, they have to decrease to about zero in order to have temperatures stop rising. So these graphs that I'm showing you are coming from this simulation tool, which I'll talk more about in future lectures. So it's this thing called EnRoads, Energy Rapid Overview and Decision Support. And I'll just show you that it's kind of cool that you can use this to play with various scenarios. So here's the graphs I was showing you. Here's our four graphs: global population, GDP per capita, energy intensity of GDP, carbon intensity of energy, and then CO2 emissions. So if you look at global population, there's a little knob for global population that you could play with. There is a knob for GDP per capita. And then you can look at energy efficiency in terms of transport and buildings and industry. And then energy intensity or carbon intensity of energy would be over here, like your coal, oil, and natural gas, for example, or if you want to change how many renewables or nuclear or some type of a new technology. So it's just useful to be able to kind of play with this and say, okay, population growth, like what if population growth was, instead of 11 billion, closer to 13 billion at the end of the century? So now we're up here. What does that change? Well, it's not going to change these three terms. But what's that going to do to CO2 emissions? Oh, it would increase it by, something like 20% or something like that. But you go from 80 gigatons of CO2 per year at the end of the century to 100 gigatons per year at the end of the century. So that's just it's just a useful little app to have to see how these things can influence CO2 emissions. So let's look at these actual terms in terms of real data. So this is world emissions since 1960, broken up into these four Kaya terms. So the way that they do this is they just zero them all to what the value was in 1960. And so then you're looking at percent changes in each one of these things since 1960. And so we see that CO2 emissions have gone up and up and up. This is just through 2016 over this time period. And so what's driven that? Well, it's the exact trends that we just saw in those previous graphs, that we have this increase in GDP per capita over that time period, increase in population over that time period. So we've seen these emissions increasing because of increasing population and because of increasing wealth, just people consuming and producing more goods and services. And so CO2 emissions have increased despite the fact that we have decreased our energy intensity, our energy per unit of GDP, or basically we're getting, more efficient at producing goods and services. And despite the fact that we have decreased our carbon intensity slightly. So carbon intensity kind of was decreasing, down here, and then it's basically flat globally since the year 2000. So that might be surprising if you hear, kind of a lot of hype about wind and solar and renewables. And it's just the case that globally, those things have not really taken over yet. So in certain locations they have, but globally they have not. And they've been basically overwhelmed by factors like China developing kind of 100% on coal from the 1990s to the 2010s, things like that. So these two terms have gone down, but not nearly enough to cancel out the population and GDP per capita trends increasing. So that's for the world, but we can see some interesting regional variations. So what about for the United States? So here's for the United States. Here is our CO2 emissions in the United States and the 4 factors that contribute to that. And what's interesting about this is that CO2 emissions in the United States kind of peaked in 2007 about. And why did they do that? Why have they been going down since then? It's not because population has been going down since then. So population has continued to rise since 2007. GDP per capita, so we had this is the Great Recession, but GDP per capita has increased since then, until of course our new COVID recession or possibly depression. So that has increased over that time period. But what has decreased is the carbon intensity of energy. So in the United States, we have largely moved away from coal and towards natural gas. And so per unit of energy, natural gas emits far less CO2 than coal does. And so that's good. And then also just efficiencies have increased. So our energy per unit GDP has gone down as well. And so over this time period, since 2007, we have seen a decrease in CO2 emissions. And this decrease in CO2 emissions, despite an increase in GDP per capita, that's what we really want to see globally, right? We want to see the developing world be able to develop, be able to have a high standard of living without their CO2 emissions increasing. So this is kind of a sign, a glimmer of hope that could be done. And so that in order for that to be done in the developing world, they need to develop on using energy that comes from, not from fossil fuel sources, so from renewable energy sources. And then potentially you can get this GDP growth per capita without CO2 emissions growth. And it's interesting to think about like the current economic recession or depression, whatever you want to call it, and like how much that has affected United States emissions. And so this is a preliminary estimate of annual emissions, annual CO2 carbon dioxide emissions updated through 2020. So this is guessing what's going to happen the rest of the year in 2020, and then a guess for how that kind of recovers in 2021. And so this is showing what I showed in the last graph, that CO2 emissions kind of peaked in 2007 and has been going down. And so we're seeing this decrease in emissions from 2019 to 2020. But I just want you to notice how small of a decrease that is. And what that is telling me anyway, is that campaigns about reducing consumption are not going to make all that big of a difference in terms of CO2 emissions if your underlying energy system still uses fossil fuels. So if you could imagine like a climate campaign that was like, okay, the problem with CO2 emissions with climate is that we have too much economic activity. So what we're going to do this year is essentially what happened in COVID. We're going to everyone's going to stay home all the time. No one's going to go to work. Everyone's going to telecommute everywhere. No one's going to fly. You're going to stop buying a bunch of stuff that you would have bought. We're going to increase unemployment so people have less money to buy goods and services. We're going to slow down manufacturing. We're going to do all these things. And you might think, well, that's really going to reduce emissions a lot, right? And this is all you get out of that. Plus, obviously it's so much pain for people economically in their lives. And so this is it's a very interesting experiment about how much changes in consumption are going to affect CO2 emissions. And it kind of shows that the highest leverage thing that we have is really replacing the fossil fuel infrastructure with renewable energy, or with something that captures carbon and doesn't allow the carbon to get into the atmosphere, instead of something that just reduces consumption. So I wanted to show you a couple other potentially good trends. So this is in the United Kingdom. And they have a similar situation in the United States where they have also had their CO2 emissions peak. So theirs peaked in like 1974, and it's not because their population stopped increasing, and it's not because they stopped increasing consumption of goods and services. So their GDP per capita has increased by 250%, their population has increased by something like 25%, but their CO2 emissions have gone down. And again, it's because their carbon intensity has gone down and their energy intensity has gone down. So they're being more efficient with the energy that they use, and then carbon intensity less CO2 per unit of energy. So there's more alternative energy being used, or more renewable energy being used. And then part of this as well is globalization, and the fact that countries like the United States, United Kingdom, are kind of exporting their manufacturing to other countries. So they may still consume an electronic good, but then depending on how you do that accounting, that could either be attributed to where the consumption is done or where the production is done. And so in this case, it's attributed to where the production is done. So it would be attributed to China, for example. And so that's where some of this decrease in emissions from developing countries also comes in. Okay, let's look just at a couple more of these. Here's France. I wanted to bring this one up because it's a little bit different than other ones. So France also saw their CO2 emissions peak in the 1970s. Again, same story, not because GDP per capita stopped increasing, not because population stopped increasing, but in this case, it's mostly due to this strong reduction in their carbon intensity. Does anyone know what France did with their energy infrastructure?
Nuclear power by a lot, and it was really good.
Yeah, so they had a national plan to scale up nuclear power, very much top-down government plan, and it reduced their CO2 per unit of energy. And so they've seen this kind of long multi-decadal timescale reduction in their CO2 emissions. So some relative success stories, but here's the big challenge: is the developing world. So here's China. And we can see China has yet to decouple, although there's kind of some signs of that here of CO2 emissions plateauing while GDP per capita is increasing. But if you look at what happened with China from the 1990s to about mid 2010s, just this explosion in CO2 emissions and in economic activity, and those two things were just tied totally together. So it wasn't that population exploded, it wasn't that these other terms exploded, it was their CO2 emissions went way up, driven by basically a developing country becoming much more developed, so much more goods and services produced. And then we're, from a global perspective, we're expecting places like India to kind of follow suit. So their CO2 emissions have been going up by a lot. And so far, their GDP per capita has not exploded like China's has. But that's kind of the trend that we're expecting, is that this to just kind of rocket up. And so in order for that to happen and for CO2 emissions not to rocket up, you really need this like carbon intensity to start dropping extremely rapidly. You need that fourth term in the Kaya identity to go way down. And so you can see on this graph, like there's not really negative percent numbers. So that has not happened for them yet. And then kind of same story in other countries, like in sub-Saharan Africa. So Nigeria is just one example. Their CO2 emissions are going up, but we are expecting in the coming decades that GDP per capita is just gonna explode in places like Nigeria. And so if that's gonna happen, again, and we want CO2 emissions to level off and come down, then we need carbon intensity, the CO2 per unit of energy, to decrease by a lot. So not developing based on fossil fuel infrastructure.